dear students. So in the electrochemistry, this is the second last topic and second last concept, electrochemical cells, batteries and fuel cells. Although concept all of you have, gone through the concept involved in this fuel cell and electrochemical cells, batteries, but just it is a factual part of this chapter. So a little revision is required for this because some like lead storage battery, if you take an example, so that is a particular type of electrochemical cells I'm talking about. So this is, you can say, examples of the commercially available electrochemical cells. Conceptually it is over, but this is a fact based information. So all of you are knowing that in the electrochemical cells, redox reaction is taking place and electrons are transferred from reducing agent, I mean reducing agent, and you know that reducing agent is called fuel, to the oxidizing agent indirectly via an external circuit. So this is the basic concept. So redox reaction is taking place here. Redox reaction is taking place inside the electrochemical cell. Electrochemical cell. See, electrochemical cells. If you connect so many electrochemical cells in the series, then this is called what? Battery. So electrochemical cells, batteries, right? Where electrons are transferred transferred from reducing agent this is called fuel, to the oxidizing agent from reducing agent indirectly via external circuit circuit to the oxidizing agent right? So this is the net summary of the working of electrochemical cell. See, one reducing agent is there, means which oxidize, means lost the electron. Other one is the oxidizing agent, means which reduce, the species which reduce. Both were kept in a different containers or different chambers, and they are externally and internally connected. So this is the total story of electrochemical cell. right? And if different electrochemical cells are same electrochemical cells, basically we are trying to add the same electrochemical cells so that the potential difference will not make up any problem. So I mean, similar electrochemical cells when are connected in the series, then it is called battery, right? See, we have different types of batteries or electrochemical cells, right? One which are non-rechargeable. Non-rechargeable means once the amount of chemical energy is stored, once it is converted into electrical energy, no further chemical energy can be converted into electrical energy. So such type of reactions, such type of cells are called irreversible cells or batteries, right? And second are the rechargeable, and the rechargeable cells are electrochemical cells. Once they attain the state of rundown state, then again we can recharge them. They are called secondary cells. So primary cells, you can say. So types of this electrochemical cells are batteries. See, primary, primary cell, you can say primary cells are non-rechargeable. They are non-rechargeable, right? Non-rechargeable. That is irreversible. That is irreversible, right? They are called primary cells. Once the total chemical energy which is stored in this cell is converted into electrical energy, no further chemical energy can be converted into electrical energy, right? So at rundown state means we can say after rundown state means delta G is equal to 0. Further, chemical energy cannot be converted into electrical energy. Electrical energy, right? So they are called primary cell. Okay, so let's see some examples. So the first primary cell, we can say that is copper zinc Daniell cell. Hmm? That is if we see the example, so copper zinc Daniell cell, Daniell cell, right? And well-known example of primary cell is zinc carbon dry cell, which is common. Voltage of this is 1.1 volt, 10 volt typically, and the voltage of this is 1.5 volt. So this zinc carbon dry cell, which is used in torch battery and for various purpose, it is used in our daily uses. So see what is the net representation of this zinc carbon dry shell. All of you are knowing this Daniel shell, working of this Daniel shell, copper zinc, and here this is zinc carbon. Zinc is anode, carbon is cathode. Here carbon, in fact, graphite anode we are using, cathode we are using, and this is what inert kind of cathode. So see the representation, we are taking Zn solid, and the electrolyte we are taking ZnCl2 and ammonium chloride. All these are in the form of aqueous paste here, and MnO, MnO2 solid, and MnOOH, and carbon graphite, right? So this is negative terminal of the cell, and this is positive terminal of the cell. Sorry, this is negative terminal of the cell, this is anode, and this is positive terminal of the cell, this is cathode. Okay, so hopefully all of you are clear, and you just see the fact, because we are talking about example, we are not talking about the general concept. So what should be the anode reaction here? The anode reaction is like this. The anode reaction is like this. Zinc solid plus ammonia. This will reacts with ammonia. This ammonium chloride means ammonia. Basically, ammonia is the acting. You can write here NH4 plus, no problem. But ammonia is the acting species here. So you will get zinc, ammonia whole twice, 2 plus plus 2 electron. This reaction is taking place, right? And cathode reaction is MnO2 plus NH4 plus 2 electrons gives MnO OH, okay, plus Mn is reduced here, plus ammonia. So balance this equation. So 2 electrons, 2 NH4 plus, so 2 ammonia. So you have to multiply whole equation with the 2, right? Okay. So this is the reduction equation. Now overall reaction is, see, add this Zn solid plus 2 MnO2 plus 2 NH4 plus plus 2 ammonia cancel, 2 ammonia is left, 2 electron cancel, Zn NH3 whole 4, 2 plus 2 MnO OH, right? So this is the net reaction, and see, zinc here it is 0, here it is plus 2. So in this reaction, zinc is oxidizes to Zn2 plus, zinc oxidizes to Zn2 Mn here 4 plus, and here Mn3 plus, right? So Mn is converted from plus 4 to plus 3, right? So this is the, I mean, net redox reaction, and these are the species which are involved in this oxidation and reduction. And the result of this, you will get the EMF from the cell is 1.5 volt, and minimum it is reduced to zero point 0.8 volt. After reaching 0.8 volt, it is not uh, further usable, right? That is low enough, so you cannot convert this further into chemical energy into electrical energy. Now see, there are so many modifications time to time taking place in this basic dry cell. We are trying to improve the shelf life and voltage. So one major success we get when we make this electrolytic medium is alkaline. And nowadays all of you are heard about this alkaline battery like that. So once we make this medium is alkaline, we take here some strong alkali like NaOH, KOH, then its voltage and shelf life both will increase, both increases, right? So we can see here dry cell alkaline. So a modification in this basic dry cell alkaline dry cell or battery. So what is the representation of this? See, the representation of this is zinc solid, ZnO solid, OH minus. See, this is alkali. And here in the cathode side, we are using MnO2, and here we are getting MnOH whole twice. Instead of getting MnOOH, we are getting MnOH whole twice, and here carbon graphite, right? So this is positive and this is negative, right? So now what is the voltage is here? Voltage is 1.9 volt, right? Close to 1.9, means 1.6789 depending on the preciseness and other factors, ideality of condition. So what is the anode reaction here? The anode reaction is zinc solid plus OH minus. This will give you the ZnO plus H2O plus 2 electron. So 2 OH minus. Okay, now it is balanced. And what is the cathode reaction this time? The cathode reaction is MnO2, right, plus 2H2O plus 2 electrons gives Mn OH whole twice, right? MnOH whole twice plus 2 OH minus, 2 OH minus, right? So I think all these things are balanced. So what we can write here, overall reaction Zn solid plus MnO2 plus H2O. This H2O, one H2O is left, 2 OH cancel. two electron cancel, Zn plus MnO2 plus H2O gives ZnO plus MnOH whole twice. So this is the overall reaction, right? And you can use uh, here in place of zinc. I mean here what you can see that zinc is oxidizes from 0 to plus 2 and Mn is plus 4 to plus 2, right? Plus 4 to plus 2. Mn reduced from plus 4 to plus 2. So this is the overall reaction. So little bit difference is there. See here plus 4 to plus 3 is it is going, and here it is from plus 4 to plus 2, right? And the shelf life of this I mean cell is much larger than the simple dry cell. And here in anode some alternative materials you can use. In place of zinc you can use cadmium, you can use aluminium, and cathode some alternative materials you can use like silver you can use as a cathode, mercury, iron, lead, iron, right? Mercury. This you can use nickel. Yes, nickel also you can use as a cathode. Alternative source, alternative materials. But the graphite is the best. Graphite is the best. Why we are going to use silver as a cathode? In that sense, I mean, have a definite lifetime, because this is a irreversible cell. Once it discharge, you cannot further use this. So why we are going to use? Although if the use of silver make this cell longer half life, 10 years, 20 years, then we can think of that, okay, we can use cathode of silver cathode, right? But here along with this purpose, usefulness of the conversion of chemical energy into electrical energy, some economics also an important factor, right? Pricing is also an important factor. So this is dry cell, right? And now secondary cell, we will start secondary cell. See, secondary cell, secondary cell. So the secondary cells are batteries. They are rechargeable. Rechargeable, and you can say they are reversible, right? So these are secondary cell. They are called secondary cell, and once they are discharged, then again we can recharge this and further we use. The best mm, known, what you can say, of the well-known secondary cell is the lead acid storage battery. Lead storage battery, but it is better to write lead acid storage battery. Right? Lead storage battery. And 2 volt typically. So we are adding so many electrochemical cells in the series. So each electrochemical cell consists of 2 volt here. So 2 volt per cell, right? 2 volt per cell, not the 2 volt per whole unit. You know, whatsoever in our house this inverter batteries are used, so typically they are 12 volt or 24 volt. So 12 volt is commonly used batteries, big batteries. So they have 6 such cells connected in the series, right? So overall voltage you will get 12 volt, overall voltage 12 volt. Now see how this is constituted. What is the representation of this cell? This is very unique cell. PB solid will give PbSO4 aqueous, H plus aqueous, HSO4 minus aqueous, and PbSO4 solid and Pb. So which type of cell you are looking for this? This is a type of concentration cell. This is a type of concentration cell, right? So this is cathode and this is anode. Again I am making mistake. This is cathode and this is anode, right? And this representation I have shown here when this is discharging. So this is the representation when this is anode, this is cathode. When there is discharging means when chemical energy is converted into electric. Discharging means chemical to electrical. Chemical to electrical. And when this is recharging, in the charging state, when this battery is charged, then this is what cathode and this is anode, reverse. So that's why this is called reversible cell. And all this voltaic cells, they can be made reversible by applying some external voltage, as all of you are knowing. So this is the discharging state representation and charging state representation, right? When in charging state, these all these anode cathode are reversed, right? So it is clear. Now see what how to this reaction, anode and cathode reactions are represented. See, anode reaction, Pb solid plus HSO4 minus. Remember, this HSO4 minus will work because in this case density of this H2SO4 is very important. If density is less than some threshold value, your cell working will be affected and voltage accordingly will affect. So HSO4 aqueous, this will give you the PbSO4 solid plus H plus 2 electron. See, this is anode reaction in lead storage, lead acid storage battery, and cathode reaction is like this. Cathode reaction is like this: PbO2 solid. See, I have forgotten to write here PbO2. So please add here PbO2 solid, PbSO4, right? Okay. So PbO2 solid plus 2, plus H plus, this H plus plus HSO4 minus HSO4 minus. This will give cathode, means plus 2 electrons, plus 2 electrons. This will give PbSO4 solid plus 2H2O. 2H2O. Now see the balancing, 2 to the 4H. So here we have to 2H plus 2 HSO4 minus and 2 PbSO4 and 2 PbO2, not 2 PbO2, right? PbO2 plus no, PbSO4 and 2 3H plus 3 and 1 4. Okay, so make it 3H plus 3 and 1 4 to the 4. Okay, 4 2 2. I think it is balanced. Okay, so this is what happening inside the lead acid storage battery. This is anode reaction. This Pb is converted into PbSO4, and here also this PbO2 is also converted into PbSO4. Okay, so what oxidation and reduction is taking place? See, from here this is 0 oxidation state and this is plus 2. So this is equation 1. And which reaction I am writing here, charging or discharging? This is discharging. 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 Right? Equation 2 also, this is discharging. Discharging. Right? And okay. And here this is converted from plus 4 to plus 2. See, all the species related to lead. Lead is converted into lead 2 plus and lead 4 plus is converted into lead 2 plus. Okay. Now what is the complete cell reaction of this? The complete cell reaction for this is complete cell reaction is, now see here, Pb solid plus PbO2 solid plus 3H plus and H plus, so only 2H plus is left here, plus 2HSO4 minus 2HSO4 minus will give you PbSO4, 2 PbSO4 plus 2H2O, right? So this is the net reaction. This is the net reaction, and many times due to rise in temperature, this water evaporates. So time to time you have to add some water here, right? Which helps in the ionization of these ions. Now see, if you see total moles of electrons involved in this reaction, complete reaction, N is equal to 2. And here if you see 2H plus plus 2H HSO4 minus is equal to 2H2SO4. So 2 moles of H2SO4 requires 2 moles here in this reaction for complete reaction. So you know N factor for this H2SO4. What is N factor here? And many people are doing mistake here. The N factor is here for H2SO4 is equal to 1. Never write N factor for H2SO4 is equal to 2 in this particular reaction. So this is the purpose of my discussion here, that why I have specifically, particularly I am discussing this. You know, N factor is defined as the moles of species involved in any reaction per mole of electron, for 1 mole of electron. So 2 moles of electron, see here, 2 moles of electron lost in the oxidation and gain in the reduction. So total 2 moles of electrons are involved with respect to the 2 moles of H2SO4. So for 1 mole of H2SO4, only 1 moles of electrons are involved. That's why from beginning we are not writing here SO4 2 minus. HSO4, we are writing here HSO4, HSO4, this is the reason. So here the N factor is 1, not 2. Remember this is very, very important point. So the N factor for H2SO4 in this reaction, N factor for H2SO4 in this reaction is equal to 1, right? Okay, now see in the charging, what will happen when this cell discharge. Then again, if you want to charge this, then the reactions are reversed. Now this becomes what anode. So when you reverse this reaction, first reaction, so charging, this is the homework for you people. Homework, write the charging reactions of lead acid storage battery with the anode and cathode. How to get reverse the equation 1 and 2, right? So if you reverse the equation 1 and 2, then you get the equation for charging of this lead acid storage battery, right? Now see this concentration and density or specific gravity of H2SO4 is very important for this lead acid storage battery. See, this is the safe range of H2SO4 density. This from here to here for the this is the safest range for the use, right? When there is a discharge process is taking place, see here, this is the discharging. So once the discharging going on means when the battery is in use, the density of H2SO4 is decreasing. So this is the 100% charged state where the percentage of H2SO4 is 36% and the density is slightly above 1.25. So once the discharging, so this is the optimum charged state, maximum, and now density will decrease gradually. So by measuring the density of this H2SO4 solution in the battery, we can assess how much chemical energy is still left in the system and when it requires further charging. So this when discharging will take place, then we move from here to here. So we can write point 1, point 2. So 1 to 2 when you are moving. So this is the charging state. Charging means now the density will increase. Density is increased because the reverse reaction. Now sulfate, and it is very evident here. Don't try to remember. See, lead and this H2SO4. This H2SO4 is combining with the lead, and you know this is precipitate. Lead sulfate is insoluble basically. So sulfuric acid, the component of sulfuric acid is going to precipitate, so obviously the density will decrease. And when you reverse this, then this lead sulfate will decompose into the sulfate, so density will increase. This is the simple concept here. So in the discharging, density, in the charging, density will increase. And from 2 to 1, 2 to 1, this is the charge. Sorry, discharge, right? So the optimum percentage of H2SO4, it is usually we are taking here 40%. You can remember like this 40% is okay, the concentration of H2SO4 required, right? And accordingly, if the concentration is less than 40%, then you have to add more H2SO4 for a better efficiency of your battery. Now see, lithium cell, lithium ion cell. See, in all computer and mobile phones, usually lithium ion batteries are used. So I don't know the exact, what nowadays are used, but what basic fundamental I am telling you that see, what is the anode reaction here? Anode reaction is simple. Lithium solid is converted into lithium ion plus electron, and cathode reaction is Li plus cobalt oxide COO2 plus electron. This will give you the Li plus COO2 minus, right? So this is the discharging reaction. Discharging, and this is also discharging reaction. And during charging, this is the simple reaction, and in the charging, recharging, this reaction will reversed. So this is a lithium ion battery. Main components I have shown here. Nowadays, many companies are involved to improve the life of battery, but see, I'm telling you the what fundamental equation which is involved in the lithium ion battery, right? So one more cell is left, that is called fuel cell. And in fuel cell, they are also very important fuel cell, because a great advantage of this use of this fuel cells in the space aircraft, right? So fuel cells are very important. See, fuel cell. So fuel cells basically see, various variety of fuel cells are used. So first I am telling you when acidic fuel cell, I mean acidic condition, and second one I will tell you the basic medium. And obviously basic medium is better than acidic medium, right? So hydrogen oxygen fuel cell, one of the most popular fuel cell, hydrogen H2 and O2 fuel cell. This is most popular fuel cell. And what the other requirement, platinum electrodes, costly platinum electrodes. And second requirement is acid electrolyte, and acid electrolyte we are basically we prefer H3PO4 rather than H2SO4, right? And see what is the anode reaction. Both the electrodes are from platinum. So anode reaction is in the fuel cell is 2H2 gas gives 4H plus 4 electron, right? So this is anode, means negative electrode, and cathode means positive electrode, that is O2 gas plus 4H plus 4 electron. This will give you the 2H2O, right? So this is the cathode reaction. So now overall reaction, what overall reaction you will get here? Overall reaction is 2H2 gas plus O2 gas will give you 2H2O liquid, right? So this is the net reaction. So you are using, we are using hydrogen as a, I mean one fuel, oxygen is another fuel. So you take hydrogen and oxygen, and on the consumption of hydrogen and oxygen you will get what? H2O, right? H2O liquid. And this H2O you can use because this is the very pure form of water we are getting here, right? So this is the simple acidic, I mean simple H2O2 hydrogen oxygen fuel cell with acidic electrolyte. Now with basic electrolyte, what reactions are changing? So H2O2 fuel cell with basic electrolyte or alkaline electrolyte. Net reaction is same. There is no difference in the net reaction, right? But I mean half reactions are little bit changed. So anode reaction is like this: 2H2 gas plus 4OH minus. This will give you the 4H2O liquid plus 4 electron. And cathode reaction is O2 gas plus 4H plus 4 electron gives the 2H2O liquid, right? Only anode reaction will change, cathode reaction is same. So the overall reaction is so 2H2 gas plus O2 gas and 4H plus 4H2O, 4H2O left hand side, and here 6H2O, so 4H2O will go, so 2H2O is left, so you will get 2H2O. So see the net reaction, there is no change in the net reaction. And you know this space shuttle, in space shuttle this alkaline electrolytes are used, because you know alkalines are less harmful for humans and other skin, but acidic acids are very much harmful for us, right? So that's why in the space aircraft this one is used, right? So space aircrafts or space shuttles, this is used. Okay, and here oxidation of hydrogen is taking place and reduction of oxygen. Okay, so this is the all about, and you know the problem of water can be also solved here by using this fuel cell, right? So there is no problem. And some other fuels, some other gases like methane and other gases also can also be used in place of this hydrogen and oxygen. Not necessarily only hydrogen and oxygen, because see the only product is water here in hydrogen and oxygen. That's why we prefer this hydrogen oxygen fuel cell, but not mandatory. You can use any gas, right? So gas to gas, you will get the different product and different voltage, right? Now see this advantage of the fuel cell. So first advantage, this is longer shelf life. They have longer shelf life, and you can use these cells for a longer time. Second advantage is there is no pollution free, right? And we can use for longer time, and in the space aircraft or space shuttle, for heat and light energy we are using, and we are getting a pure form of water, so that we can use for drinking purpose. So these are the different advantages of this fuel cell, right? This is the advantages of fuel cell. Okay. Well, dear friends, see there is one question based on this lead storage, lead acid battery. See, in a lead acid battery, the electrolyte taken is 39% H2SO4 by mass with density this grams per ml. The battery holds 3.5 liters of the acid. So we are assuming here that this volume remains, constant during the charge and discharge. There is no change in the volume. We are assuming that. During discharge, the density decreases to this. So from this 1.294 grams per ml to this, which is 20% H2SO4 by mass, right? So first option we have to calculate here moles of H2SO4 lost during the discharge. So how to make the solution of this? See, before discharge, first we make the quantitative calculation before discharge. So before discharge, we can find the mass of solution. So mass of solution is equal to density of the solution into volume of solution. So volume of solution is 3.5 liters. So 3.5 liters multiplied by 1.294 1.294 grams per ml. So we have to convert this into ml. So this will come to equal to 3500 ml multiplied by 1.294 grams per ml. So ml to ml cancel. So we will get how much? This mass 4529 gram. So this is the total mass of solution, means in this H2O plus H2SO4 both are present. Right now, this is 39% H2SO4 mass. So we can find out the mass of H2SO4. Mass of H2SO4 is equal to 39 by 100 multiplied by 4529. 4529 gram. So this is equal to 1766.31 gram. So total H2SO4 initially it was present this. Now do the same calculation after discharge. So after discharge, what will happen? Mass of the solution, because density changes, so mass also changes. Mass of solution is equal to density of solution into volume of solution. This time also we are taking the same volume. So this is 3500 ml into density changes to what? 1.139 grams per ml. So this is equal to 3986.5 gram. Right? Now this time mass of H2SO4. So mass of H2SO4 is what? 20% of this. So this is 20 by 100 into 3986.5. So this is equal to 797.3 gram. Right? So in this before discharge and after discharge, so what is the moles of H2SO4 lost during the discharge? So basically this is not lost, this is converted into lead sulfate. So moles of first part, moles of H2SO4, not lost here, not the proper word lost, moles of H2SO4 converted into lead sulfate. So in this you can see here that mass of H2SO4 converted. So mass of H2SO4 converted is equal to initial mass of H2SO4 minus final mass of H2SO4. So initial mass was what? 1766.31 1766.3 gram minus 797.3. So this is equal to 969 gram, right? So moles of H2SO4 converted is equal to 969 by 98 by 98. So this is equal to 9.88 moles, right? And this much moles of lead sulfate also produced. So if the question is asked, okay, how many moles of lead sulfate are produced? The same 9.88 moles of H2SO4, I mean lead sulfate are produced, right? Now the molarity of solution after H2SO4, after discharge. So molarity of H2SO4, molarity of solution with respect to H2SO4. So molarity with respect to H2SO4 is equal to moles of H2SO4 left in the solution, divided by volume in liters. This is the formula, right? So moles of H2SO4 left in the solution is equal to how much mass is left after discharge. Mass of H2SO4 left is 797.3 by 98. So you will get 797.3 divided by 98. So this is 8.13 moles. So this is equal to molarity of H2SO4 is equal to moles 8.13 divided by 3.5. So divided by 3.5. So 2.32. So this is the answer of the second part. Now third part, what they have asked? Amount of charge. See, amount of charge. So amount of charge produced is equal to N into F, right? You know, moles of electron, if you see how many moles of electrons were there. So total produced moles of electron, produced. See here, N and F is the charge over 1 mole of electron. So if we are going to use this formula, and N is the moles of electron involved in discharging process. How many moles of H2SO4 are involved in the discharge? See, this moles 9.88 moles. So there is the moles of electron involved in the discharge of our conversion of 9.88 moles of H2SO4. So as we know that 1 mole of H2SO4 involves 2 moles of electron in discharge or charging process, as from the equation. From where I have taken this? From equation, from net cell reaction. This is important. So that's why in the beginning I have told you that cell reaction is very important. So 9.88 moles of H2SO4 total involved in this discharge process. So 9.884 moles of H2SO4 is equal to 2 into 9.88. Right? So this is the value of N for this moles of electron. Moles of electron. So the amount of charge produced is equal to, this is equal to 2 into 9.88 moles multiplied by 96500 coulombs per mole. So moles and moles cancel, so you will get what? 2 into, this is what? 9541, 78 coulombs. 78 coulombs. So this is the answer for the part C. Now part D. So ampere R is equal to Q by 3600 second. In number of seconds in 1 hour. So we have calculated this 954178 divided by 3600, right? So this is equal to 265.05. So this is the answer. Right? So in this way you can calculate all these calculations related to the lead acid storage battery. So this is the question, and